What is up, everybody? Yes! New chapter, new lecture. Good. Chapter 3, Orbital Perturbations. So if you remember thus far, we have always considered the two-body problem. Or in other words, we had always considered that the orbital plane was inertially fixed, and that the orbit within this plane was fixed. Okay? And this is due to the fact that we had neglected all perturbations that are naturally affecting the motion of the spacecraft as it orbits around the Earth. We had neglected drag. We had neglected solar radiation pressure. We had neglected the oblateness of the Earth, micrometeorites, the moon attractions on spacecraft, and so on and so on. So in practice, or in reality, the orbital elements are all time varying. There's no such thing as a constant semi-major axis, because the semi-major axis will over time decrease a little bit due to the fact that drag is reducing the energy of the spacecraft. The eccentricity will change also with time, and so is the right ascension of ascending node. So all those orbital elements that we had considered thus far as being constant are in reality changing with time due to the effects of orbital perturbations that are pushing and pulling our spacecraft as it is orbiting around the Earth. Okay, so this is what this chapter is concerned with, and that is orbital perturbations, chapter 3. Okay, so what we're going to do in this chapter is essentially derive a methodology that will allow us to analyze the effects of any perturbations, some random perturbations that we can think of on the orbital elements, and specifically on their rate of change. Okay, so we will be seeking expressions for dA dt, the rate of change in our semi-major axis, the E dt, rate of change in the eccentricity, the I dt, rate of change in inclination, the capital omega dt, rate of change in Rayan, and finally the omega dt, rate of change in argument of perigee. Okay? And the tool that will allow us to do so is known as the Gauss Variational Equations. So again, the Gauss Variational equations are a set of 5 equations that will allow us to predict the rate of change in our orbital elements that are no longer constant because we are now considering the effects of natural perturbations on the spacecraft. The I dt, the Rayan dt, and the argument of perigee dt. So that is to say that the orbital plane will shift in 3D space, and that the orbit within the orbital plane will also rotate a little bit as time goes on. Okay? So let's go back to our two-body equation of motion that we had derived previously, the most fundamental equation in this course. Minus mu r vector over distance between m1 and m2 cubed. And that is for the two-body problem, because as it is, it's only the primary body attracting the spacecraft toward itself, or accelerating the spacecraft towards itself through this contribution here, which is mu of the primary body. But here we want to take things to the next level and make things a little bit more realistic by considering a net perturbing acceleration vector. This is what this extra term denotes in that equation of motion. So the net perturbing acceleration. So this is the combined effect of drag, solar radiation pressure, which is the interaction with the sun's photons on the spacecraft itself, which is kind of slowing the spacecraft a little bit. The effect of the oblateness of the Earth, and all the other effects you can think of, micrometeorites and so on, affecting ultimately the acceleration of our spacecraft. Okay? And more precisely, we're going to see expressions for the rate of change in those 5 orbital elements, which will be function of 3 things. Those 3 things, I'm going to say function of Fr, F theta, and Fz. And same for the other orbital elements. Rate of change in eccentricity, function of Fr, F theta, Fz, and so on and so on. Now, what are Fr, F theta, and Fz? Well, those happen to be the x, y, z component of this extra term, which captures the effect of all perturbations combined together. So the x, y, z components of this vector, but in which reference frame? The answer is the orbital reference frame, denoted by our good old calligraphic capital F symbol, like that, transpose times Fp in orbital reference frame, like that. So I've just written this particular vector, which is the net perturbing acceleration vector, in terms of its components. In which reference frame? Well, in the orbital reference frame, denoted by this guy here. Or in other words, we're going to say that x, y, z components of this extra term that we've added to our two-body equation as x, y, z components of Fr, F theta, and Fz. This is how we shall denote, again, the x, y, z components of this particular vector inside the orbital reference frame. And the reason why we're not choosing Fx, Fy, Fz, which would be also an intuitive way to write those components down, is because the orbital reference frame, through its definition, you will understand in a minute why it is relevant to write those as Fr, theta, and Z. Okay? So that is the objective of 3.1. The Gauss Variational equations are those equations here, essentially. The time derivative of our orbital elements as a function of x, y, z components of the net perturbing acceleration vector. Okay? But first, let's have a look at the orbital reference frame such that we can then derive the Gauss variational equations themselves. And that will be in section 3.1.1. Orbital reference frame. So if you remember the perifocal reference frame, you will have an easy time understanding this one because it's almost the same. So if you have an elliptical orbit, like this, okay, and you have M1 at a focus. Well, if you remember our perifocal reference frame at its px unit vector in the direction of the perigee of the orbit, its py unit vector straight up, and its pz normal to the orbital plane pointing at you. So that was the definition of perifocal reference frame. And that reference frame was independent of the spacecraft's position because, as you can appreciate, its x-unit vector always points at the perigee, which is essentially a fixed vector in 3D space, okay? So that reference frame was inertially fixed. Whereas now, if we have our spacecraft, say, over here, orbiting around M1, then the orbital reference frame will have its x-unit vector always pointing at our spacecraft. So that will be OX, okay? Or in other words, OX is always along the position vector R, like this, right? So as the spacecraft orbits about M1, R vector follows the spacecraft, and then so will OX. So OX is not inertially fixed, but will track the spacecraft through its orbit. OZ will be normal to the orbital plane, and in fact will be collinear with PZ. I'm going to say OZ, normal to the orbital plane like that, and OY will simply complete the triad through the cross product as usual, okay? So then you could say that OX is actually in the same direction as R, the vector, but then because OX is a unit vector, we need to scale R vector with its own magnitude like that. We're going to say that OZ is normal to the orbital plane and actually in the direction of our orbital angular momentum vector H over its own norm to make sure that OZ happens to be a unit vector. And then OY will be given by, surprise, surprise, a cross product of Z with X. Boom, just like that. Okay? One thing to note is that the angle between the orbital reference frame in green and the perifocal reference frame in black in this figure is one angle, and that angle happens to be our true anomaly. So when true anomaly is equal to 0, we have OX along PX, OY along PY, and OZ is always along PZ anyway, so that doesn't change. So we're going to say that the relationship in terms of rotation matrix between orbital and perifocal, so COP, COP, is actually equal to principal rotation about the Z direction, C3 or CZ, it's the same thing. Through which angle? Through theta, which is our true anomaly angle like that. Okay? Now, at what speed is the orbital reference frame spinning around like that? Well, it only depends on the rate of change of our true anomaly theta. So we're going to write that omega of the orbital reference frame with respect to the perifocal reference frame can be expressed in terms of vector and its components, say in the orbital reference frame, like that. But the good news is that the x, y, z components of this particular vector that defines the angular rate of orbital with respect to perifocal is only along one axis. And that axis is the axis of rotation, which is the axis coming straight at you out of the board, or along PZ, or in other words, along OZ too. So we have 0, 0 for the x and y components of the angular velocity vector here. And along the z component, all we have is theta dot, the rate of change in true anomaly, or the instantaneous rate of change in true anomaly. Okay, so just to be sure that we're all on the same page, the angular velocity vector omega OP coincides with PZ and coincides with OZ. So those three vectors are normal to the orbital plane. They're pointing right at you again. Excellent, excellent. What else can we say? Well, we can easily see that inside the perifocal or inside the orbital reference frame, the components of our position vector will always be along OX only, correct? Because OX is always in the same direction as R. So there's no way that R vector, which is in blue, can have either a Y component or a Z component, because R is always dead center on OX. So our position vector expressed in the orbital reference frame will simply be R, 0, 0. Okay? So just the length of this vector projected on direction OX only. Or again, in other words, it is impossible for our vector to have a direction or a component along OY or OZ. Furthermore, we could look at the velocity vector of the spacecraft, described in terms of its components in the orbital reference frame. And all we have to do it is take the time derivative of our position vector R, like that. I'm going to come back there and say, okay, this is a vector, so I need to apply the chain rule because it's a vector times a column matrix. So that would be time derivative of the transpose of the Vectrix related to the orbital reference frame times the x, y, z components as they were before, plus the Vectrix orbital reference frame transpose times the time derivative of the x component, y component, and z component, which both stay equal to 0. And all this is for the speed or the inertial derivative of our position vector expressed in terms of its components in the orbital reference frame, although in its current form it's not that easy to play with, or it's not that clean. So what we're going to do is to keep playing with that relationship a little bit and end up with something quite a bit nicer in the end. And the reason why I look specifically at R and then R dot is because we're going to need those variables in the subsequent section, which will come, in which we will derive the Gauss Variational equations themselves. Okay, so we'll have already derived those things. We'll just plug and play in the near future. R dot. So does anyone remember what is the time derivative of a Vectrix? Yes. You are absolutely right. This is the angular velocity vector cross product with the Vectrix itself, okay? And which angular velocity vector? Well, in that case, omega OP cross product with the Vectrix transpose, okay? All this is for Vectrix time derivative times R 0, 0 plus Vectrix transpose R dot 0, 0. All right, so what is this vector in terms of its components in the orbital reference frame? Turns out we had already looked at this particular vector, so I'm going to swap it out with its definition in orbital directly, which is this, 0, 0, theta dot, if you remember. This is a vector, so I'm going to say cross product with another vector, like this, then plus Vectrix orbital reference frame times r dot 0, 0. Okay, so I can then factor out my Vectrix orbital reference frame transpose out of those three items and write this, which multiplies a bunch of component operations, right? So here we had the cross product of one vector with another one, but then because we took the Vectrix out of it, it becomes a cross product of components. And if you remember chapter 1, cross product cannot be applied to components directly. It has to be applied to vectors. So the cross product is a vectorial operation, but the equivalent in terms of components is the skew symmetric matrix. I'm going to write components like that. And then the skew symmetric matrix times R 0, 0, and then plus R dot 0, 0. Excellent. So all there needs to be done now is to figure out the skew symmetric matrix, which is a square 3 by 3 matrix that is being built or constructed or assembled based on a 3 by 1 column matrix like that. And if you go back to chapter 1, you will see that to do it, I'm going to prepare a 3 by 3 because this is what this gives me. You have always the zeros on the lead diagonal. Here you're plugging minus the z component, which is theta dot. Here you have the positive y component, which is 0. And here you have minus the x component, which is 0 again. And here this is positive z, negative y, positive x, like that. Okay? This multiplies then R 0, 0 plus R dot 0, 0. Good. Moving forward. So you see it's nothing too difficult. We're just applying what we learned in chapter 1 in terms of matrix and vectors and components, and then doing a bit of linear algebra in between, and that's essentially the bulk of the work here. Okay, so 3 by 3 times 3 by 1 gives me a 3 by 1 equal to this times this, so 0, this times 0 plus this times 0, so this is 0. Then here, we're going to dot, so theta dot times r plus 0 times 0 plus 0 times 0, 0 times r, 0 times 0, 0 times 0, so this is 0 again. Plus r dot 0, 0. And hopefully you'll remember from chapter 1 that adding two components in terms of x, y, z. Well, all you have to do is to sum up the x components together, then the y components together, and then the z components together. So x is going to become 0 plus r dot, and followed by theta dot r, and then finally 0. And all this gives you the x, y, z components of the velocity vector seen in the orbital reference frame. Yes, all good. Does it make sense? The answer is yes. It makes sense because here we can clearly see that we don't have any z components. And turns out that the velocity vector is a vector inside the orbital plane at all time. And as such, it will never have a z component, only x and y. So that makes total sense. Great. So now we have derived expressions for omega OP in terms of its x, y, z components in the orbital reference frame. We have derived an expression for the position vector r in terms of its x, y, z components in the orbital reference frame. And now we've just derived an expression for the velocity vector in terms of its x, y, z components as seen from the orbital reference frame. Good. Now we have all the tools to proceed with the next subsection, which is all about deriving the Gauss Variational equations. And that will be section 3.1.2. Gauss Variational Equations, GVEs. Because I'm a bit lazy, as I told you in the past. Okay, so the starting point to derive, and again, the Gauss Variational equations are the dA dt, dE dt, the I dt, the ρn dt, the omega dt, as function of fr, f theta, and fz, which are the x, y, z components of the extra term we added to the two-body equation, the perturbing acceleration term, as seen in the orbital reference frame. Okay, so let's start off by going back to our perturbed equation of motion. So the first term is just a two-body contribution, so just primary body in the spacecraft, to which we added our perturbing acceleration vector Fp. As a first step, I'm going to take the dot product of that equation on both sides with r dot. Just like that. That's one thing. The other thing is that if you go back to chapter 2, we had obtained something very similar, which was r double dot dot product r dot plus mu r vector r cube dot product r dot, and we had said that that was exactly equal to d dt of our orbital energy, which was specific kinetic energy and specific potential energy, like that. Do you see a similarity between this and this? Is it r dot? Yeah, sorry, I forgot the dot here and the dot here. Right? I took the dot product with r dot on all terms here. And chapter 2, we have done the same thing in order to arrive to this relationship in the end. Okay? So if you can see the similarity between that and this, well, you can flip this term on the left-hand side and then make it equal to this. This is quite neat, because if the left-hand sides of those two equations happen to be equal, it means that the right-hand sides also need to be equal, which means that the rate of change in specific orbital energy is no longer equal to 0, but a direct function of the perturbing acceleration vector. Wow. So just by adding this extra term to our two-body equation of motion, we've now discovered that the energy of the orbit is no longer conserved. That makes a lot of sense. If you think about a big spacecraft with huge solar panels that are facing the flow as it is orbiting in low Earth orbit, well, drag will just reduce the energy of that spacecraft at a very rapid rate. And what's going to happen is that the spacecraft will enter a spiral descent and eventually burn down or come down through the atmosphere. Okay, so the energy is not being conserved, obviously. Okay. Yeah, so again, this is our orbital energy, or specific orbital energy, for which we also had another expression. I'm going to write but. Also, we have specific orbital energy equal to minus mu over 2a from before. Remember our discussion on energy? We had used that expression to derive interesting facts about energy and speed back then. So what I'm going to do is sub out this with minus mu 2a to write d dt minus mu over 2a equal to net perturbing acceleration vector dot product with r dot. All right. Now the time derivative of this guy ends up being the same as the time derivative of a, which is on the denominator, times mu over 2a squared. All right, so all this is still equal to fp vector dot product r dot. Okay, so we're gonna keep that result in our back pocket for now. And then we're going to focus our attention on the left-hand side, on the right-hand side only, to write that fp vector dot product with r dot can be expressed in terms of the orbital reference frame, like this. Well, actually, I'm going to go straight from vectors to so vector component operations, if you will, because we know that the dot product of two vectors give us a scalar, obviously, and that scalar is going to be equal to the components of the first vector transpose times the components of the second one. So I'm going to write, this is fr, f theta, and fz. Yeah. Those are the x, y, z components of the first vector transpose, and then components of the second vector. And here we had obtained the result previously. That was our r theta, r theta dot, and 0 like that. So then we can say that this dot product is going to give us a scalar equal to fr times r dot plus f theta times r theta dot. Interesting. Do we have expressions for r dot and r theta dot? Yes, we do from chapter 2 actually. Such that we can write that this is equal to r dot, f r. R dot was our square root of mu over p times eccentricity times sine theta plus f theta times r theta dot in terms of magnitude was equal to square root of mu over p. This times 1 plus e cos theta, like that. So this is for the right-hand side of that expression. Which means that we can rewrite that expression we had. So dA dt mu 2a squared equal to all this elegant expression on the right-hand side. Okay? Now, our objective here was to derive an expression or an analytical expression that would allow us to predict the rate of change in our orbital elements as a function of fr, f theta, and fz. So in other words, finding or solving that expression first for dA dt, then doing a similar process and ending up with dE dt, and then we're doing another process for inclination and so on and so on. Okay? So that expression can easily be solved for the rate of change in semi-major axis, dA dt equal to 2a squared over mu. That multiplies square root of mu over p times e sine theta. This multiplies fr plus square root of mu over p and multiplies 1 plus e cos theta. And then this is multiplying f theta, and then close the bracket here. Okay, so obviously the next step is to factor out this term and those two guys, and we write it as 2a squared over mu times square root of mu over p multiplies e sine theta times fr plus 1 plus e cos theta times f theta, like that. There's not much we can do with what's inside those parentheses, but what we can do is to further simplify this by writing it as the square root of mu p on the denominator, just like that. And that gives us the rate of change in semi-major axis as a nonlinear function of fr and f theta, or in other words, this is the same as dA dt equals function of fr, f theta, and fz, which is indeed the first Gauss variational equation. Right? Now, fear not, I'm not going to do the entire process for the remaining orbital elements. I'm just going to give you the answers to those. And something to be aware of is that although we're seeking, generically speaking, expressions for rate of change in orbital elements, function of fr, f theta, and fz, it doesn't mean that the x, y, z components of our perturbing acceleration will always have an influence on all orbital elements. For example, here we've just discovered that only the x and the y component in orbital reference frame of our net perturbing acceleration acting on the spacecraft is influencing the semi-major axis of the orbit. And that makes a lot of sense because the semi-major axis is a measure of the orbit within the orbital plane. So a perturbing acceleration which is normal to the plane would not have any impact on that specific orbital element. Okay? I'm just going to give you the other equations instead of doing similar development. So you have for dE dt, rate of change in eccentricity. You have the square root of P over mu multiplies sine theta times the x component of the perturbing acceleration seen in the orbital reference frame plus 2 cos theta plus E times 1 plus cos theta squared all this divided by 1 plus E cos theta, and this guy multiplies f theta. So as you can see, the Gauss variational equation for the eccentricity is not function, again, of the z component of the perturbing acceleration, which is fz. Only the in-plane components of the perturbing acceleration have an impact on the eccentricity, which is the shape of the orbit within the orbital plane. So that makes kind of sense too, okay? Now note that the rate of change in eccentricity depends on the orbital position of the spacecraft, quantified through the true anomaly. It depends on the size of the orbit through P, which is function of semi-major axis, and also depends on the eccentricity itself. So the rate of change in eccentricity depends on the eccentricity. That is just to say that in MATLAB Simulink, if you want to simulate the behavior of the eccentricity as function of time, you would get the Gauss variational equation for eccentricity, which calculates the E dt. And then what you would do is integrate that to get the actual eccentricity and feed the result back into the Gauss variational equation to calculate the new rate of change. Integrate that, get the new eccentricity, feed it back, calculate the new rate of change, integrate new eccentricity, and so on and so on. So this is a closed loop process or simulation that you would have to carry out to then ultimately take the signal and plot it as function of time. Okay? Eccentricity function of time, you'll probably see it decreasing because of the drag effect. Okay, and that was the same for, I shouldn't have erased it, but the same for the Gauss variational equation for semi-major axis. which was function of the semi-major axis itself. Good. Now, Gauss variational equation for inclination is given by square root of P over mu times cos argument of perigee plus true anomaly, which is also known as your argument of latitude. This is u, okay, over 1 plus e cos theta. This times the z component of the perturbing acceleration in the orbital reference frame, or Fz. So this is the first time that we see that the z component of the perturbing acceleration has an impact on an orbital element. Okay. Turns out that the inclination is not affected at all by the x and the y components of our perturbing acceleration. This is for I. For Rayan, d Rayan dt, the GVE for this one will be square root of P over mu times sine of argument of latitude, or omega plus theta, if you will, same thing, over sine of inclination times 1 plus e cos theta times the z component. Okay, so similarly, Rayan is only function of the z component of the net perturbing acceleration. And finally, the only orbital element that depends on all x, y, z components of the perturbing acceleration is the argument of perigee. This is d omega dt equal to square root of P over mu, open a big bracket. So we have minus cos over the eccentricity, multiplying the x component, or Fr, plus 2 plus e cos theta times sine theta. All this divided by e times 1 plus e cos theta. And this is what multiplies the y component of our perturbation, and then minus sine of argument of latitude, omega plus theta, divided by tan of inclination times 1 plus e cos theta, close the parenthesis, and this is whatever multiplies the z component of our perturbation, like that. So if you want to be really accurate in numerical simulations, what you would have to do is to do not only one channel like that, but you'd have to repeat it and simulate the variation of all orbital elements at once. So GVE for I, then another block that will calculate the GVE for A, and so on and so on. Rate of change, inclination here, integrate it, 1 over s, the inclination, but then not only you feed it back in here, but for example, let's see, yeah, argument of perigee is function of inclination. So if that is GVE for argument of perigee, that you use to get d omega dt, integrate 1 over s, and get omega, feed it back. While this one also requires the inclination in the computational process. So instead of taking the inclination as being a constant, you could very well take it as the output of this Gauss variational equations for I, okay? So I comes in here as well as omega, and so on and so on. So you could couple them all together as you see fit, or as is needed through those Gauss variational equations. Make sense? Clear as mud? Perfect. let's keep moving. Knowing the rate of change in orbital elements could be very useful, but something which is even more useful is to use them to determine what's known as secular variations. So let me explain you what secular variation refers to. So, if you were to plot the change in Rayan over time, if you consider you have a perfectly or a Keplerian orbit, which is another word to say that you are considering the two-body problem, Rayan, as all the other orbital elements, will remain constant. It's not being affected by anything because all you have is a primary body. But now you're throwing additional perturbation to it, and all of a sudden, Rayan will start to vary as a function of time. Something like that, for example. I don't know. Okay? So d Rayan dt, what that gives you is the instantaneous rate of change at any instant based on the current value of Rayan and based on the current value of all the other orbital elements. But this rate of change varies with time. Here, the slope is much greater than, say, here. So d Rayan dt is actually not a constant, but a function of time. Okay? And at some other time, the rate of change could be negative, positive, much more positive, almost zero, and so on and so on. Okay? So the output of your Gauss Variational equation will vary with time. Well, what is very useful to calculate is what's known as the secular variation. And that is the net change in your orbital element that you're looking at, calculated over one orbital period exactly. So this is t equals 0, and this is t equals 1 orbital period. You look at the initial value for Rayan, and the value here at t equals 1 orbital period later, and the net change is referred to as delta Rayan, like that. And this is what we call secular variation, which is same thing as net change over one orbit in terms of radian. Okay? So d Rayan dt would give you something in radian per second, whereas the net change would be just radian. Okay? The rate ascension of ascending node shifted by pi over 3 radians over one orbit, for example. This is the secular variation, which you could obtain through visualizing a graph like that. But you can actually calculate it based on the Gauss Variational equation by taking the integral, right? Or in other words, you could say that secular variation in semi-major axis will be the integral of my Gauss Variational equation over time. And that time we're going to let it vary between 0 and 1 orbital period. And do the same for all other orbital elements. Between 0, 1 orbital period later of d Rayan dt, which is your GVE for Rayan, or Gauss Variational equation, dt, and so on and so on. That's one way you could calculate the secular variations in any orbital elements through the use of your Gauss Variational equations, which are the time derivative term of your orbital elements. All right? Turns out that doing it this way is a lot more complex than taking the integral from 0 to 2 pi of d through anomaly. Okay? So although this is technically correct, to simplify our life, we are going to look, and I'm going to switch color because my black marker is about to die on me. So let's switch to blue, for example. So it turns out that taking the integral from 0 to 2 pi of dA dt, or d theta like that, is a lot simpler than that version. And similarly for any other orbital elements, here I just use Rayan as the example, 0 to 2 pi of d Rayan d theta over d theta. But gee, it was so nice here. We had already expressions for these guys, these terms. Here we don't have any clues about what they are. These are not the Gauss Variational equations in any way, shape, or form. What do? Well, you just have to remember that, so if you look at semi-major axis for the following development, dA dt through the just a simple multiplication can be obtained as dA d theta dt. It's the same thing. Just cancel out the d theta terms on the numerator and denominator, and boom, you're back on your feet with dA dt. Okay, so what you're telling me is that this is dA d theta times, what is d theta dt? Well, that is just theta dot, the rate of change in our true anomaly. Cool. So then I know how to get my dA d theta, or my d Rayan d theta, or my d whatever d theta. The trick is just to take my Gauss variational equation, dA dt in this specific example, and then divide it with theta dot. Okay? So that is a transformation we have to do up front before we can even think about doing the integration from 0 to 2 pi over d theta. All right? So just for completeness, I'm going to rewrite how to calculate the secular variations. And let's use another one, say of inclination. Then again, what you have to do is the integral from 0 to 2 pi of your Gauss Variational equation, di dt, but then divide the result with theta dot, like that, in front of the integral. And d theta. All right? Actually, let's pull the 1 over theta dot inside the integral. Just like this. Because your theta dot is actually a function of theta, so that's why we need to pull it back into the integral here. So we're going to say that where theta dot, well, that is very difficult to evaluate whenever we are considering perturbations affecting the motion. But here, if we assume that the perturbations are kind of small enough, then we're going to use the expression we had derived in chapter 2. And we're going to approximate theta dot as being square root of mu p over r squared. Okay? So I say approximately equal although before it was exactly equal in chapter 2, but approximately equal here because of the perturbing acceleration, which would change the rate of change in true anomaly slightly from that ideal value that we had obtained back then with the two-body problem. Yet, this is the best we have at that point. So if you want, again, coming back to our discussion on secular variation, if you want, say, secular variation in inclination, you use the expression I gave you for the GVE for inclination, divide that with theta dot, where theta dot is this, and then do the integral from 0 to 2 pi over the integrating variable, which is true anomaly. Okay? And the process is the same for, the other orbital elements, obviously. But for conciseness, I'm not gonna write those all out. This and this. Just never forget to divide your Gauss Variational equation with this factor. Otherwise, the result will be way off. Okay, and I see a lot of students making that mistake in an exam. It's just something to remember, okay? Something else you can look at after obtaining the secular variations is to get the average rate of change in a specific orbital element. Okay? So say you have, again, coming back to the same graph that was Rayan at the time. That looks something like this, for example. This is your starting value at t equals 0. If that is the value at t equal 1 orbital period later, then again you know that the net change here is your secular variation. The instantaneous rate of change is essentially the slope along the way that you get directly from the Gauss Variational equation, like this. But another thing you can obtain is the average rate of change. So you draw a line between the final value after 1 orbital period later and the initial value here. And you say that my average rate of change, which is denoted by this and that with the orbital element and dot, is just your secular variation in radians over 1 orbital period in seconds, okay? So it kind of gives you a rough idea of how is the orbital element is changing its function of time by averaging the slope as a constant instead of looking at the instantaneous change, which is what the GVE are giving you. So you just draw a straight line and you call it the average rate of change. And you fill the blank with the orbital element in question. In that case, this is in Rayleigh, okay? Just don't forget that this is always calculated over 1 orbital period exactly, and not half orbital period or 2 orbital periods. By default, it is always a secular variation, which is the net change after 1 orbital period divided by 1 orbital period in seconds, okay? So that concludes this introduction to orbital perturbations in terms of deriving the fundamental tool that we have at our disposal to analyze the effects on any kind of perturbations, right? All we need to do to use the tool, which is the GVEs, is to figure out the modeling of the perturbations such that we can extract FR, F theta, and Fz, so the x, y, z component of the net perturbing acceleration as seen in the orbital reference frame. And once we have those 3 components, or those 3 scalars, all we need to do is to plug these back into our Gauss Variational equations, which will allow us to predict at what rate will our orbital elements vary as function of time. That were the dA, dt, dE, dt, di, dt, and so on equations. And then based on that, we can go 2 steps further. The first step is to look at the secular variation, which is the net change in a given orbital element after one orbital period. And then we can take another step, and that is to look at the average rate of change in our orbital element by simply dividing the secular variation by one orbital period. Whew, okay, so I hope that that kind of makes sense to you and that you are appreciating all the results we did ahead of time. And again, all we're doing here is to build upon the foundation we had set in Chapter 1 and also in Chapter 2. We're just making things a bit more realistic here. All right? Thank you, guys. Thank you for listening. I'll see you next time. Bye-bye.